お待たせいたしました。
Thank you for your patience. It is time to begin the offshore wind webinar co-hosted by Carbon Trust and ClassNK. I will be serving as an MC for today's webinar. My name is Yamaguchi from Kensi. It is nice to meet you all. Today's event is held online via Zoom in Japanese and English through simultaneous interpretation. At the bottom of your screen, please click on the globe and choose Japanese or English. Today's webinar is on offshore wind measurement and floating LiDAR technology. And here is the program. Excuse me, it is not shown on the screen, but after the opening remarks, it will be followed by introduction, keynote speech, and Q&A. And today, right before this seminar, you must have received a reminder email, which is attached with a program CV of presenters and PowerPoint deck for the keynote speech. Please download them for your convenience. As of yesterday, over 900 people have signed up for this seminar. We are excited to have this many people as audience. Thank you very much. As for questions, they can be asked anytime during the webinar using the Zoom Q&A function. In the final Q&A part, we are going to take as many questions as possible. When you ask a question, if you don't mind, please let us know your name and your company. We also have prepared a questionnaire for you to fill in. You can also ask questions related to today's presentation in the questionnaire. We're going to address them and the remaining questions on Zoom at a later date. This webinar is going to be for about an hour. Please bear with us till the end. Now, first, I would like to invite Mr. Junichi Hirata, the General Manager of Innovation and Sustainability Center, ClassNK, to give opening remarks. Now, Mr. Hirata, the floor is yours. Good afternoon. My name is Hirata. And now, please allow me to give an opening remarks. So today, thank you very much for joining the seminar co-hosted by Carbon Trust from the UK and ClassNK. We have already held a couple of webinars, but today's webinar is a special one. Now I would like to pull up some slides. Can you pull up my PowerPoint slides? Can someone pull up my PowerPoint slides? Thank you. Next page, please. Please turn the page. At the beginning of July, well, we always have worked and collaborated with Carbon Trust to solve social issues of Japan, including carbon footprint. And this time, to support promotion of offshore wind power generation, we decided to conclude an agreement at ClassNK. With this agreement, we are willing to contribute further to the Japanese society and also the offshore wind industry. And if you go to the next page, Carbon Trust since 2009 has been running a project called Offshore Wind Accelerator. and has been leading the offshore wind industry in Europe. So Carbon Trust is cooperating with many entities which will be able to cover almost the entire Europe geographically. And here's the next page. In ClassNK, since around 2010, we started a program of wind turbine certification. This was when wind power generation industry was just about to begin, and there was no certification program. And as you can see on the map, since then, we have seen establishment of offshore wind farms one after another. And various projects have been promoted with assistance from the government in order to promote wind power generation. So Carbon Trust and we, ClassNK, with expertise in the Japanese industry, are now collaborating together. Carbon Trust has an expertise as a pioneer in driving wind power generation through their program Offshore Wind Accelerator. So through this collaboration, we are aspiring to contribute to promotion of wind power generation. Next page, please. So this is the final page of my presentation. So when we look at the seas around Japan, we are excited to see more wind farms in the sea around Japan through collaboration with Carbon Trust. And this is the very first webinar since the exchange of this agreement. And we are also willing to continue to hold this kind of seminar in the future. And we're looking forward to seeing you again in the future. Now I'd like to hand back over to the facilitator. Thank you.
Mr. Hirata, thank you very much. ClassNK and Carbon Trust collaborate together in offshore wind power, and we are able to witness that they are working together for the decarbonization of Japan. And now moving on, the next speaker is Dr. Fei Fremantle from Carbon Trust. He will be speaking as an introduction prior to the keynote speech. As he is fluent in Japanese, I'm hearing that he will be making speech in Japanese. He's joining live from London. Over to you. Thank you. Good afternoon. I'm Fei from Carbon Trust. And would you please show the slides as well? Thank you very much for your attendance to this webinar co-hosted by Carbon Trust and ClassNK. As Mr. Hirata mentioned, Carbon Trust and ClassNK have concluded agreement the other day. The purpose of the agreement is to support solutions to disseminate offshore wind power generation business in Japan. In order to do that, as a symbol of the collaborative relation of the two companies, we are especially grateful to host this webinar together. Last year, we also co-hosted floating offshore wind power related webinar. It's been already a year since then, and it's incredible. I'm sure that quite a number of people have joined that webinar as well. At that time, I presented on the technology of the floating offshore wind power, but today, there is another expert of our company who will be presenting on the theme of measurement systems and related technologies. he will be introducing later on, but he is abundant in experience and in knowledge, and it is a great pleasure that he is making presentation today. First of all, we would like to briefly introduce what Carbon Trust does in the area of offshore wind power business. Next slide, please. Thank you. As Mr. Hirata mentioned, Carbon Trust in 2009, in this offshore wind power business, we have started our activities. At the very beginning, offshore accelerator, wind accelerator is what we have embarked on. This is a joint industry program, JIP, that we work together with the industry developer. This still continues now, and this is the longest GIP program that we have witnessed in the offshore wind power business. In addition to that, there are other projects. For example, a JIP floating wind JIP is another project, and there are a total of 17 companies joining in this program, and 3 Japanese companies are also joining. The companies on the right-hand side are joining JIP, and they are also joining offshore wind accelerator. Please show the next slide. Would you please click to the end of the slide? Outside of this program, Carbon Trust, in this offshore wind power industry, we are offering various types of consulting programs. As you can see on the slide, these are the services we provide. Up to now, in many of the countries, we have provided advices to the policies and technical advices, and we have provided our solutions. And the country which has the highest track record is Japan. We have embarked on our activities in Japan from 2014, and up to now, to many of the customers in Japan, we have offered these activities. Out of that, the partnership with the Japanese companies are becoming especially vital. And this time, for the first time, we have officially concluded an agreement with the Japanese company. And so with this as a juncture, together with ClassNK, we would like to provide offshore wind power related business to a large number of customers in Japan. Please move on to the next page. And the offshore wind power generation market in Japan is now drawing attention in the past few years. And in the past 1 to 2 years, finally, we have entered into an introductory stage. We have been working quite aggressively in that area. As you know, Japan has very ambitious goal, which is by 2040, they are planning to introduce 30 to 45 gigawatt. In addition to that, there is even a difficult and hard to achieve cost reduction target. Under such circumstances, it is very important to solve the challenges. On the right-hand side, you see the technology development roadmap in Japan for offshore wind power. And you will be able to see that there are challenges that need to be addressed. So a measurement system that we are going to discuss today is one of the major items. From our perspective, over a decade, offshore wind power generation business is what we have experienced. And in European countries, there are many countries which have already introduced offshore wind power generation. They have abundant experiences and the failures as well. So learning from such countries, I think there are many things that Japan can understand. And so together with ClassNK, we are hoping to share such information. So what we are going to discuss will be on the topic of measurement systems. And this is one of the elements that is important to cost. So this is going to be one of the key points. To the yield, this is an important element for predicting the yield. And this also has significant impact to financing and cost. So after this, the details will be shared by Neil. So that is all. Thank you very much for your attention. Fei-ji, thank you very much. The theme of today's webinar is one of the important elements of the Japanese offshore wind power generation projects. So now we would like to move on to the keynote speech of today from Carbon Trust, from Mr. Neil Adams. We would like to have the keynote speech on the measurement system and technology of floating LiDAR. Neil is joining from Scotland on live. Over to you, Neil.
Well, good afternoon. Thank you very much. It's a pleasure to be speaking with you today, and thank you particularly to the interpreters for putting up with my Scottish accent. If we could move on to the agenda slide. I will give a brief introduction to the Carbon Trust. I will try not to repeat what Fei-ji has said, and then move on to the meat of the presentation. So give you a little bit of an introduction to wind resource assessment as a general topic, talk about some of the measurement systems that we use in the industry, and how you might go about optimizing a wind resource assessment campaign. And then finally, just highlight some examples of these campaigns around the world. So move on to the next slide, please. The Carbon Trust is an unusual organization. We don't have external shareholders. All of the profit that we make is recycled into achieving our mission. And our mission is, as stated there, accelerating the move to a sustainable, low-carbon future. Offshore wind has been one aspect of that. Of course, there's a lot of other activity going on in the Carbon Trust. But particularly in the early days in European waters, we saw the potential for offshore wind to be a major contributor to that move to a low-carbon future. And that's really why we've been so heavily involved in it for the last 12 years or so. Next slide, please. Today, we'll be talking mainly about activities which fall under what we would call the technology innovation pillar of what we do. So particularly measurement systems, turbine systems related to the offshore wind industry. That's certainly not all that Carbon Trust does, though, to try to accelerate the uptake of offshore wind. We do a lot of work on industrial development, so helping countries, cities, areas to develop their supply chains to gain maximum kind of economic benefit from offshore wind, so make sure they get the benefit of these developments when they come. We do a lot of work with policymakers to help them shape the environment in which offshore wind can thrive. And increasingly at the moment, we do a lot of work on systems integration. So how do renewables in general and offshore wind in particular tie in with the grid, and how does it interact with other technologies such as hydrogen? That's an increasingly important topic as renewables become a more dominant part of the grid in most countries, and Japan will be no exception to that. Next slide, please. Feyzi mentioned several of the projects, or the wider programs rather, that we have been involved in and been at the heart of over the years. Within those programs, there are a few individual projects which I think are worth highlighting here, because I'll come back to several of the themes of these over the rest of the presentation. So floating LiDAR has been a strand running through lots of our work over the last several years. When we first got involved in this area back 10 years ago, floating LiDAR was not at all a mature technology. There was a lot of reticence in the industry about using it. But we saw the potential for it to give significant cost savings and perhaps to achieve some other benefits as well. So to that end, we have undertaken several activities to try to make that technology commercially acceptable, and I'm very glad to say that now it is. So within that, we had, I guess if I start in the top right actually, a number of trials of the technology, so demonstrating that we could both obtain accurate measurements from floating LiDAR systems that gave us wind data that were equivalently accurate to what we could get from a met mast, and also that the systems could survive these harsh environments out at sea. In parallel with that, we worked with several partner organizations to develop a roadmap for the commercial acceptance of floating LiDAR. So setting out the steps that the technology must go through, and understanding what the developers and users of that technology have to demonstrate for banks to be able to accept the data that are produced. Again, as part of that same effort, we have worked with a number of external organizations to put together a recommended practice for floating LiDAR. So this explains how the technology should be deployed, what to look out for when you are contracting a floating LiDAR service or purchasing a piece of equipment, how it should be deployed, how the data should be interpreted. And these three activities really fit together, so that they give an assurance for the technology as a whole, and they've really helped push forward the commercial acceptance of floating LiDAR. Floating LiDAR, though, is very far from all that we are involved in. So if I can highlight the middle panel there, we have worked on technologies such as scanning LiDARs from shore. So the image there shows a trial from Dublin Bay in Ireland a few years ago, where we used combinations of, well, individual and pairs of LiDARs onshore to measure the wind resource at a number of points offshore and validate that against other measurement assets and demonstrate the uncertainties that could be achieved with such a technology. And drawing all of that together, we have worked for various project developers to help them draw on all of this expertise in different measurement systems and define what's best for their sites. So in the bottom right there, I've highlighted one report that went to New York State Energy Research and Development Authority, highlighting how these technologies and others could be used to help New York State adopt offshore wind power. Next slide, please. So what is a wind resource assessment? I'm conscious we probably have a very wide mixture of experience amongst the audience today. So for some of you, this will be a rather basic high-level view, and for others, I hope this is a very welcome introduction to the topic. There are many reasons why you might want to measure the wind, and I think in Carbon Trust we have an interest in all of these at different points. We've done a lot of R&D campaigns that have involved very high-tech, sort of bespoke approaches to taking measurements, for example, inside or around wind farms. That's not what we're talking about today. What we're focusing on today is measuring the wind resource at a site before a wind farm is built. So it's that resource assessment step only. And for that kind of campaign, there are really three requirements. So first of all, it has to be bankable. What do I mean by that? Well, the purpose of the campaign is to gather enough data such that financiers are willing to lend money to build a wind farm. So there are very large amounts of money at stake. There will be a high level of due diligence applied. There will be a very rigorous look at uncertainties, and the campaign needs to be designed such that that due diligence can be satisfied. So we need to achieve a high quality, low uncertainty, traceable estimate of the long-term wind resource. Secondly, we need to understand site-specific risks. So wind turbines are designed to a certain set of environmental loads. We need to be confident that the loads which they will experience on the site in question fall within that design envelope. And that relies on on-site measurements and then some extrapolation techniques to understand what the worst case winds over certain recurrence periods will be, and the worst case wave and tide conditions as well. The final criterion is all this must be done while minimizing cost. The wind resource campaign happens early in the life cycle of a wind farm development. It's entirely possible that you will commission a resource measurement campaign on a site that turns out not to be viable for, well, either for reasons of wind resource or for other reasons. So there is a risk of sunk costs here. There's a large risk on the project in general. So it's important that costs are minimized at this stage if possible. Next slide, please. So how do we go about assessing the wind resource at a site? In terms of measured data, there are really two strands to this. So the top images on the right there are site data. So we have on-site measurements either from a met mast or a floating LiDAR or some other system over a period of typically 2 years or something of that order, that give you a very high quality measurement of the site, of the wind conditions, sorry, at one point on your site. That only lasts though for a couple of years, and you know yourself that there are windy years and less windy years. There are windy parts of a site and less windy parts of a site. So we need some way of extrapolating from those data out to a long-term wind resource. And the way that's usually done is using a process called measure, correlate, predict, where we have simultaneous data from some long-term reference source. Now, usually that's an onshore meteorological measurement site. There are plenty of them dotted around coastlines in particular in the UK, and I'm sure in Japan as well. In some cases, very far offshore, this has been done with long-term reanalysis data, so or mesoscale modeling data, rather than a specific measurement site, but that's much less common. So we take the simultaneous measurements from those long-term reference sites with the specific measurements we've taken on site, form a regression between those two, a correlation, and then use the long-term reference data to predict the long-term wind resource at our site. And that's usually expressed in something like a windrow shown on the left there, which is really a probability distribution of wind speed and direction at the site. Next slide, please. That windrows is really the critical driver for calculating your energy yield. So you will already know the power curve of your wind turbine that you want to install, or perhaps you have a few candidate turbines in mind. So you will have a power curve similar to what's shown in the center of this slide. You can effectively multiply up the wind speed distribution on the windrows with that power curve to give you a gross energy yield. And that's the energy yield that would be achieved if every turbine saw the free stream wind and if the turbines were available all of the time. Of course, that doesn't actually ever happen in practice. So from that gross energy yield, we have to subtract a number of losses of different types, and that becomes our net energy yield. Next slide, please. One of the most important losses that we need to consider is wake losses. So this is down to the aerodynamic interactions between the wind turbines. So when you have one wind turbine sat downwind of another in its wake, it will produce less power. We can model that in a number of ways. And again, this is an area in which the Carbon Trust has been very active over the years in developing and validating wake models. And that gives us a prediction for the wake loss. There are then a number of other losses which need to be subtracted from the gross energy yield to give us our net. But again, in many cases, these are driven by met ocean conditions of one form or another. So for example, your availability loss may be driven to some extent by the sea state that you measure on site. So yes, our wind resource measurement campaign or met ocean conditions in general are critical to understanding our net energy yield. Next slide, please. When we predict a net energy yield, there are a number of uncertainties in that estimation. The perfect model will give you an answer which is, well, has a 50% chance of being too high and a 50% chance of being too low in a given period. And it's somewhat humbling for model developers to think of it in that way. There is a spread of potential outcomes around that central estimate, the center estimate being what we would call a P50, so a 50% chance of being exceeded. 6 of the main uncertainties, which are usually highlighted in any bankable wind resource assessment, are the uncertainty on the site measurement. So no measurement technique is perfect. There will be some intrinsic uncertainty on the data that you collect, whether that comes from an anemometer on a met mast or a LiDAR or something else. The historical wind resource used for that measure, correlate, predict process drives some of the uncertainty. There are really 2 parts to that. So one is the intrinsic measurement uncertainty of the wind resource data themselves, and the other is the quality of the correlation that we see between those long-term reference data and the data captured on site. If the correlation between them is very good, then you would expect that long-term reference data to be representative of what happens on site. If that correlation is poor, then it's not, and that obviously feeds through to a much greater uncertainty on the energy yield at the site. Usually less of an issue offshore is a vertical extrapolation. So if your measurement system doesn't extend as far up as hub height, then there will be some extrapolation between the highest measurement point and the hub height, assuming some level of wind shear, which entails an uncertainty. Much more common offshore is a significant horizontal extrapolation uncertainty. So we measure at one point on the site, and if you have a large wind farm site with particularly a significant gradient in the wind resource across the site, which is common near shore, then that extrapolation feeds through to an uncertainty in your overall energy yield. There is an uncertainty due to the future energy variability. So depending on the period of the future in which you're interested, excuse me, there's an uncertainty that comes about just through the interannual variability of the wind. So if a financier is particularly interested in the first couple of years of operation, there's a chance that those years will be particularly windy or particularly calm, even if your long-term wind resource estimate is correct. That's an uncertainty that needs to be factored in. And finally, there are uncertainties on performance losses. So we talked about wake models a minute ago. Those models are not perfect. We in Carbon Trust have done a lot of work to drive down the uncertainties associated with them, but there is still an uncertainty there. And that feeds through to an uncertainty in the final wind resource. Depending on how the project is financed, these uncertainties will be factored into financing decisions in different ways. So very commonly, a debt financier will look at what they call the 10-year P90. So the energy yield has a 90% chance of being exceeded over the first 10 years of the project's life. That is a kind of safe level for them to look at. The reason for that is that a debt financier really has 2 outcomes. So either everything goes according to plan and the project developer is able to make the repayments as expected, or they can't. So there's a risk on the downside side of uncertainty that they see, because if there's too much of that downside uncertainty, the repayment will not be made. On the flip side, they do not see any benefit if the wind farm produces more power than expected. That all goes into the equity investors. So this uncertainty ends up having a significant effect on the cost of capital for the wind farm, simply because equity is more expensive than debt. And therefore that feeds through into whether that site is financially viable or not. So when you're designing a wind resource assessment campaign, you really can be deciding whether or not a wind farm is viable or not. And your campaign design ends up being a trade-off really between the cost of the campaign up front, the duration, how long it will take, and the overall uncertainty, which feeds through into this financing and the viability of the site as a whole. Next slide, please. When we first became involved in this area, excuse me, about 10 years ago, there was really one technology for offshore resource assessment, and that was a met mast. An example shown on the right here. So we would have wind speed measurements from several cup anemometers at several different heights, and usually the one at the top of the mast there would be at or around hub height, and that was your most important, most valuable measurement source. You may fit other measurement systems to that. So for example, profiling LiDARs, like the ones that might be used onshore, but primarily it was all about the cup anemometers, and for wind direction, of course, wind vanes. The parameters which are important to energy yield, so atmospheric stability and turbulence, and you might include some atmospheric stability measurements on board a met mast too. So measuring, for example, temperature gradients, air-sea temperature difference, or using high-frequency ultrasonic anemometers to understand turbulence and turbulent fluxes. In parallel with that, you would usually deploy some sort of wave measurement device, whether that was a laser-based system from the net mast itself, or a separate wavebuoy, acoustic Doppler current profile, or an AWAC, to measure waves and current. So yes, 10 years ago, this is very much the gold standard of wind resource measurement offshore. Next slide, please. I'm glad to say that's no longer the case. So floating LiDAR systems are possibly an order of magnitude cheaper for a site. So cost estimates vary dramatically depending on water depth and a number of other factors, but yeah, something like 1/10 of the cost to deploy floating LiDAR instead of building a met mast. LiDARs give you a fundamentally different measure of the wind. So you use the Doppler shift on the backscatter of shining a laser through the air to give you an estimate of the radial wind speed along that laser path. And you combine those types of measurements in a number of different to give you an estimate of the wind vector. So when you take a measurement of the cup anemometer, that's a measurement at a single point. When you measure with a LiDAR, those points are dispersed in space, effectively in a cone around your measurement device. That means you have slightly different characteristics in terms of what you measure, particularly in terms of turbulence. But in terms of the mean wind speed, you end up with data which are completely comparable to what you would get from a cup anemometer. So the advantages of floating LiDAR is much lower cost. You can measure to higher heights more easily, so you can get up to top tip height and beyond. You can move these devices around the site to mitigate that horizontal extrapolation uncertainty, which I mentioned earlier. And you're not significantly constrained by water depth. There are, of course, implications for mooring design as water gets deeper, but the technology is fundamentally the same, and the cost impact of that mooring is much less significant than, for example, building a monopile for a met mast in deeper water. There are some disadvantages as well. So you tend to have a slightly higher intrinsic uncertainty on the measurements, and that really comes about because of the way in which the LiDARs are calibrated. So you usually confirm the accuracy of a floating LiDAR by comparing it to a met mast. So you can't ever achieve a lower intrinsic uncertainty than the measurements from that met mast. the other uncertainty, or the other disadvantage rather, is that the turbulence data are not directly comparable with what you would get from a met mast. The wind industry has really grown up with with turbulence data from cup anemometers. So the data from a LiDAR, while they're not fundamentally more or less correct, if you like, they're just not directly comparable. So, for example, the turbulence data that are used to specify the design criteria for met mast and for wind turbines in the IEC standard are all based on what you would get from a cup anemometer. Next slide, please. There are some other options. So scanning LiDARs from shore, they are again much lower cost than a met mast, not necessarily lower cost than a floating LiDAR, but that depends on what you choose to deploy and how. Again, you have some of the advantages that you have with a floating LiDAR, and that you can measure up to top tip height and beyond. You can mitigate horizontal extrapolation uncertainty to really quite a large degree, and you're not at all constrained by water depth. But you have some significant disadvantages. So these systems have a range of typically a few kilometers from shore. Manufacturers will often tell you up to 10 kilometers, but that's really in ideal conditions. You tend to find that in realistic atmospheric conditions that the range is a bit shorter than that. You're in 6-7 kilometers typically. There's nowhere near as much commercial acceptance of scanning LiDARs from shore as there is of floating LiDARs. Part of the reason for that is that there's much more variability in how you might configure a measurement campaign using scanning LiDARs. And the intrinsic uncertainty of the system really depends on that configuration. So are you using 1 or 2 or perhaps even 3 LiDARs from shore to measure the same point simultaneously? What are the angles of the beams? How good is synchronization between systems? There are a lot of different factors that you need to think about in the campaign design, and they are all pretty critical to the overall uncertainty that is achieved. I mentioned for floating LiDARs that the turbulence data are not really comparable with or not directly comparable with cup anemometers. That is even more true for scanning LiDARs, and again, it's strongly dependent on how the systems are configured. And finally, a scanning LiDAR system on its own doesn't give you any information on wave and current data, so you would need to deploy an extra sensor anyway to capture those data. Next slide, please. In many cases, the optimum campaign design actually involves a combination of measurement assets. So you might choose to take advantage of an existing met mast offshore somewhere, even if it's not in the ideal position, or perhaps even build a short net mast in a site where it's cheap to do so, for example, if there's somewhere with very shallow water, and combine that with a floating LiDAR system. The met mast would give you the low intrinsic uncertainty from a cup anemometer. The floating LiDAR system would give you a way of mitigating that horizontal uncertainty, which might be very significant for specific sites. If there is no cheap way of doing a met mast on site, you might do the equivalent with 2 floating LiDARs. So keep one stationary to give you a good long-term reference and move the other around the site, again, to mitigate a horizontal extrapolation uncertainty. You could even do a met mast plus some scanning LiDARs. So use the met mast at a known point offshore to calibrate the data from the scanning LiDARs and demonstrate the uncertainty that's present in those data, and then use the scanning LiDARs to capture data at a number of other points across the site to mitigate horizontal uncertainty. Really, in all of these cases, it's a point I'll come back to in a minute, there is no one optimum campaign design for every site. So it's a site-specific issue, depending on water depth and therefore costs, depending on how near shore you are, and therefore whether scanning LiDARs are at all feasible, depending on the horizontal variability of the wind that you expect, the duration of campaign that you can afford to use, and a number of other factors. So yeah, all of those effectively feed into this trade-off between cost, duration, and uncertainty. Next slide, please. So how would we go about optimizing a campaign, given that there are so many options? So first of all, we would want to understand everything about the site that's already known. So for example, understanding the constraints on the site, so technical, financial, legal, schedule constraints, and really devising a series of options that may or may not be suitable. We would assess the likely cost of each, and we'd assess the likely uncertainty from each. And we'd end up with a plot something like what's shown on the right there, where each red dot represents one campaign design option. And you see this typical trend where the more you spend, the lower uncertainty you can achieve, unfortunately. Next slide, please. There's a series of those which obviously represent the best trade-off. I've highlighted them with the blue dots and green line there. And then based on other constraints on the site development, there will be one of them that turns out to be optimal. And that's usually comes down to finance. This is shown here as quite a linear process. In practice, really, it's not. This is an iterative process, and you will go through this loop a few times to try to sort of refine the options and come up with the best approach. And you may even choose to refine further once the measurement campaign has started. You'll be monitoring the data, and there could be decisions to, for example, extend the campaign or deploy an extra measurement asset. Finally, sorry, next slide, please. I just wanted to highlight some of these examples from around the world, again, to reinforce that point that there is no one optimum solution. So the Inchcape site off the west coast, off the east coast, sorry, of Scotland, still used a Met mast, but also deployed a LiDAR. And that LiDAR, rather than being floating, was deployed on an existing lighthouse. It was there for navigation purposes. So it's a good example of taking advantage of assets that are already out at sea. The second site, which you guys were much more familiar with than I am, used a short net mast near shore and used scanning LiDARs to sort of extrapolate measurements from that net mast out to the site itself, which was further offshore. Our third example here for New York, which was again one we were involved in, used two floating LiDARs so that we could get good long-term reference and understand the variability around the site. And another American example, the fourth one there, we used one onshore LiDAR combined with two offshore systems so that we could sort of correlate what happened onshore versus offshore, and really understand those gradients between the onshore conditions, which were relatively well understood, and the conditions at the site much further offshore. Next slide, please. So I'd like to just draw this to a close with a few conclusions. So of course, a bankable wind resource assessment is essential for every project. Reducing the uncertainty means a reduced cost of capital, means a more viable project. There are a lot of measurement options now, and really the optimum for each site could be one of these or some combination of them. And there is no one sort of global solution that I can tell you today, which is the best in every case. It really comes down to a site-specific trade-off between costs and duration and uncertainty. So I hope that's been useful. That's everything from me, and I'd like to open the floor to questions and answers, please.
Thank you very much, Neil. In offshore wind projects, we've learned that there are multiple options to improve measurement accuracy and to minimize uncertainty, and that choice can be important from a financing point of view as well. So now the keynote speech is over, and we'd like to move on to the Q&A. The facilitator of the Q&A session is Mr. Hiroshi Imamura, who is a pioneer of offshore wind power generation in Japan these projects in ClassNK Consulting Service and also serves as a representative director of wind energy consulting. From Carbon Trust, in addition to the presenters Fei and Neil, we are also going to have Megan Smith, who leads the offshore wind advisory team. So we are already receiving a lot of questions, and Mamura-san suggested that we should extend the time for Q&A. So we would like to take about 30 minutes from now to address as many questions as possible. Imamura-san, over to you. Thank you for your kind introduction. My name is Imamura from ClassNK Consulting Service. So that was a very kind introduction. So we have received so many questions. So I would like to pick up some of them to ask the panelists to answer the question. So first of all, how is the wind measurement done? So there's bidding process, and a business provider is going to be selected. And who is going to do the wind measurement? Is it going to be the bidder or the project owner? It can be different in different countries, but the question is who is supposed to carry out the wind estimation? Maybe I should ask Megan to answer.
Thank you, Imamura-san. Absolutely, it does depend on the country and the policy of the individual country. So in most countries, the developer, so the project developer, will undertake the wind resource assessment. But in some countries, the government does the site surveys up front and decides to take on that role. So it does vary from country to country. Neil, I don't know if you wanted to add anything on that.
No, I have to confess I don't know much about the Japanese requirements, but yes, certainly in most countries where I've worked, yes, it's the project developer who does that.
Yeah.
Thank you very much. As a follow-up question, in Japan, there is a wind firm certification, but is there something like that in Europe? I think this is related to project certification, but at that time, with just the measurement of the floating LiDAR, is it possible to have the certification? You may not be familiar with the domestic situation in Japan, but in case of Europe, we would like to know how the certification is done. May I ask Megan to respond to this question?
So just to clarify, project certification is the planning and development or the financing? Just to make sure that I'm correctly interpreting the question.
Yes, for both of them, please.
Yeah. So the wind resource assessment process is done primarily for project financing. It's also to help understand how the wind farm itself should be designed. So that tends to be undertaken in the very early stages of project development by the project developer. And as Neil said, there are often developers will look at several sites and undertake wind resource assessments on several sites, and not all of them will go forward to full development as well. But that will be normally undertaken by the developer and done in the very early stages of project development. But the data collection will continue, whether it's through floating LiDAR data or MetMask data, often through right through the development process, because more data gives greater certainty.
Thank you very much. There are so many questions.
So let me pick up some of them. So I believe this is a question to Neil. So what is the tolerance, intrinsic tolerance for floating LiDAR? If you have any, or deviation for a floating LiDAR, if you have any figures, that will be appreciated.
So the intrinsic uncertainty on the measurements, it's usually something like 2 or 3%.
Thank you. So I believe it's for the mean wind speed, but I would like to ask another question. So how are you evaluating the measurement of turbulence using floating LiDAR, or isn't there such an assessment at all?
This is still quite a big research area to give you a proper answer to that. There are a number of approaches that we can take. So most commonly, we will have some validation data relating measurements from a floating LiDAR system to a MetMast. And there we can draw some sort of correlation between the turbulence data from the floating LiDAR system with what's measured at the MetMast. If that correlation turns out to be low scatter, even if the gradient of that line is not 1-to-1, then we can use that correlation to infer what the turbulence on site is. However, quite commonly there is a lot of scatter in that correlation, and that's because the characteristics of the turbulence change. So the turbulent eddy sizes depend on the stability conditions, for example, and that determines how those eddy sizes compare with the volume that you're measuring across with the LiDAR system. There's also scatter because in some cases the turbulence data are sensitive to the sea conditions, so wave conditions. You can imagine as your floating LiDAR system is moving around in the waves, you're measuring different parts of the sky, so you've effectively got an extra variability in what you measure simply because of that motion. In some cases, you can tease out these effects from the calibration data, but there will certainly be a much larger uncertainty on the turbulence data from a floating LiDAR system than you would get from a MetMast. Now, in European waters, that's not much of a problem anymore, and there have been enough sites built that everyone has a pretty good understanding of what the free stream turbulence you would expect offshore is. And for wake modeling purposes, that's good enough for giving us a free stream estimate. For turbine loading purposes, that ends up being a relatively small component compared to the wake added turbulence inside the wind farm. And there are standard ways of calculating that, the Franzen model from the IEC standard, for example. So we end up not being too critically dependent on getting a very accurate turbulence picture. Now, I appreciate in other climates, those rules of thumb that have been developed here really no longer apply. So we'll be more interested in assessing the turbulence on site using the floating LiDAR data. So really that's when the first part of my answer becomes relevant. So yeah, these correlations against MetMasts.
はい、ありがとうございました。おそらく北海と日本の
Thank you. I would assume that between the North Sea and Japan, I think it's different. So I think this is in Europe. And since we have so many questions, I would like to continue. In floating a LiDAR, please let us know the area of the scope where we can have effective measurement. And in relation to that question, floating LiDAR, just with floating a LiDAR, is it considered as a bankable case, or do we need to have the combination with the cup anemometer? Those are the two questions we have. So in other words, is it just considered as a bankable data with a floating LiDAR, or is it better to have the combination with the other measurement system? This is a question to Neil.
So yes, projects have been built based solely on floating LiDAR data. So yes, it's not that you need another data source as well. Yeah, projects have been financed just on the basis of floating LiDAR data. Now, those projects probably accepted a slightly higher uncertainty as a result, which would have affected their finances. But it's probably a marginal enough change to those finances that they were willing to make that trade-off. Megan, do you want to add anything to that?
No, I mean, I think absolutely in Europe, there have been a few developers who have kind of quite publicly stated that they will be primarily using floating LiDAR data only. And we kind of expect that to continue to be the case. I think there are certain situations where additional sources of data are valuable. If there's, if there's a high gradient of sort of change in wind speed across a site, or if there's a big question about turbulence, then there may be additional needs. But I think as a baseline floating LiDAR, there's no reason why any more data will be required in addition to floating LiDAR data. Just on the second question, on the effective area for measurement of floating LiDAR, I think for sort of a medium-sized wind farm, 1 or 2 measurement points is probably sufficient. I'll hand back to Neil on this as well, but it also depends on the site. So if you have quite a lot of confidence about the sort of wind speed across a site, if you're quite confident that it's not going to be higher in one area, lower in one area, maybe just from satellite data or other measurements in surrounding wind farms, then the area of confidence is larger. So it is site dependent. Neil, do you want to add to that?
Yeah, completely agree with that. So yeah, you've got satellite data, you've got, well, those satellite data tend to be used to build these reanalysis data sets, which give you some estimate of the variability. You can get a more refined estimate of that by driving mesoscale models, so weather models, running them for a few years over the site area. But yeah, fundamentally, yes, all of those things give you some estimate of how much you expect the wind to vary across the site. And if that variability is low, then there's no point trying to take a lot of measurements to cover that full area. You tend to find, of course, the further offshore you are, the less variability there is.
So we just talked about the uncertainty and the variation of the measurement data from floating LiDAR. So we are seeing some specific questions, and this is the one that I'm also interested in. In Carbon Trust, you have recommended practices for floating LiDAR. And in the experiment, semi-commercial level, well, this is the name of the specific company, but Euros and Furos, Euros and Figros, these are the companies. But they haven't reached the phase 3 level. All of the projects are still at phase 2 level. But this measurement result could be admitted as bankable if it is phase 3, but at phase 2, I believe Megan and Neil mentioned that floating LiDAR measurement data was admitted as bankable. So I see some inconsistency here. So in phase 2 and phase 3, can you also please elaborate on what is phase 2 and what is phase 3? So first of all, Megan?
Yes, I think that's a very good question and something we get asked quite a lot. The roadmap for commercial acceptance of floating LiDAR was developed to get to that point of bankability, and it was developed as a very specific industry tool. The definition of stage 2 is very detailed. We have clear KPIs, we have clear correlation requirements. And purposefully, we left the definition of stage 3 rather more broad. So it's not such a sort of tick box exercise. The reason we did that was because if it's stage 3, if it's used in a bankable project, and it will be different for different sites. So it's not really possible to certify a system as stage 3 because, for example, you've mentioned EOLOS, Fugro, they've both been used as alongside, plenty of other types of designs. They have all been used to finance bankable projects. So they are by definition stage 3 because they have been used in that way. But it may well be that you take a Fugro device and deploy it in Japanese waters because maybe it hasn't been validated in Japan. I don't know this, by the way. It may well have been validated in Japan, but because the device hasn't been validated in those waters, or because there are very sort of different metocean conditions, it is therefore not necessarily, it doesn't mean that that same system deployed in a different market is going to give the confidence to banks. So it requires more discussion. It is confusing, and it's a question we get asked a lot, and it's something we're actually looking into at the moment to try and clarify. The developers that we work with in Europe, or the developers in Europe, the funders in Europe are very comfortable with the terms, status of the systems, and understand that they are stage 3 in Europe, but not a universal stage 3. So it's a really tricky kind of language, how we present it. But I do agree, it presents confusion from external parties looking into the situation in Europe. But I'd be quite happy to say that plenty of devices have been shown to be stage 3 within Europe. Again, Neil, I don't know if you want to add any thoughts on that.
Yeah, I mean, I guess there's a sliding scale of risk in using these systems. So rather than thinking of it as 3 discrete categories of system, deploying a certain system in a certain location has some risk associated with it. And if it's an immature system that hasn't been tested extensively offshore, or uses an unknown LiDAR, or has other kind of weird and wonderful facets to it, then the risk is high. If it's one that's been used in a number of similar sites, it's been confirmed to behave consistently across those sites, and the site where you're deploying it is within that envelope where the calibrations have been done, then the risk is very low. and a lot of deployments fall somewhere in between. So yeah, it's perhaps more useful just to think of it in that sort of sliding scale of risk rather than 3 discrete categories.
ありがとうございました。やっぱりヨーロッパでは、フローティングライダーも含めて、かなりその実測データがあります。
Thank you. In Europe, including floating data, there are sufficient amount of measurement data, and you also have much experience, including mass data. So that was explained, and Megan also explained we need to verify. And I think that's partly done in Japan, including a NEDO project in Japan. So gradually, I think we are trying to accumulate the experiences in Japan as well. I think that's the current status. Thank you very much for responding to the question. I think we still have some time. So on this slide, scanning LiDAR, that is the translation, and this is the scanning LiDAR in English. And this is a case of using one scanning LiDAR, and also dual scanning LiDAR for using 2 LiDARs to measure one location. There is such a methodology. So single LiDAR and dual scanning LiDARs, can you talk about the advantages and disadvantages of single and dual? Neil, can you respond to that question?
Yes, of course. So this really comes down to why LiDARs are fundamentally different to a cup anemometer and a wind vane. The LiDAR, as I'm sure you know, involves firing a laser beam, getting some backscatter off aerosols in the atmosphere, and you get a Doppler shift in what's returned. So you're measuring the component of the wind velocity in one specific direction. That is the beam direction. So for example, if you're looking out from shore, your LiDAR just staring in a straight line and the wind was blowing parallel to the shore, you would measure nothing. You wouldn't see that mean wind speed at all. So how do you then use a system like that to characterize what the wind is doing? So scanning LiDAR systems, as the name implies, you take that beam and you scan it across some arc, and you get a set of radial velocities back. You then need to do something with those radial velocities to turn them into a velocity vector. The simplest thing you can do is to say that actually the wind velocity is the same at all of these points where I've measured. So the difference in radial velocity that I see is purely due to the angle in which my beam is pointing. So I can do some basic trigonometry, take all those measurements, do a kind of least squares curve fit type thing, and come up with a velocity vector estimate that best fits that whole set of measurements from a scan. That velocity estimate ends up being very sensitive to whether that assumption was right or not. So whether the wind is actually homogeneous across that region that you've just scanned. If it's not, so if there's some horizontal shear or some variability in the wind, whatever it may be, you can end up with an estimate which is really quite far out from reality. And one of the problems of these systems is that you're using them near shore. So you tend to have these relatively large gradients in the wind. So you need some way of mitigating that risk. And the easiest thing to do is to have two scanning LiDAR systems point the beams at the same point in space and just measure 2 components of the wind simultaneously. You still have an assumption with those 2 systems, i.e. that the vertical component is 0 or close to it, but you end up with a much lower intrinsic uncertainty if you've measured the wind at a point with the 2 systems simultaneously. I mentioned briefly in the presentation that the uncertainty ends up being quite sensitive to the design of your campaign, and that this is part of the reason for why. So if you have 2 beams measuring at a point, but the beams are almost parallel, then you get very little reduction in uncertainty from that because you've measured effectively the same component of the wind twice. If your beams are meeting at more like 90 degrees, you have a lower uncertainty because you're genuinely independently measuring those 2 components of the horizontal wind speed. So yeah, it's a complicated picture how you use scanning lidars to give you a lower overall uncertainty. Does that answer the question?
Well, I think this is really difficult to explain. And this is an additional question, scanning LiDAR, dual scanning LiDAR, and in case of a single scanning LiDAR, data acquisition rate, what is the availability of data acquisition? So availability here means I think it really is dependent on the distance from the coastline, and to what distance would this dual or scanning LiDAR be effective? Do you have any suggestion? Neil?
It depends on the system to some extent. We've got a scanning LiDAR campaign going at the moment offshore, and we're seeing typically 7 kilometers, I think. But yeah, it depends strongly on atmospheric conditions and a whole host of other factors. So yes, if you've got cloud, fog, mist, which is certainly in this part of the world very common near shore, then that dramatically reduces your range. If you actually have the opposite problem and you have very little aerosol in the air, again, that reduces your range because you don't get that same backscatter. So there's a kind of sweet spot in between, which that does happen fairly often. But I guess the one thing I would say is don't bank on getting the maximum measurement range that the device manufacturers quote all the time. You'll get that very rarely. Most of the time it'll be, I don't know, a half, 2/3 of that, something of that order.
はい、ありがとうございます。メーガンさんは、OWA の
Megan, in the development of floating LiDAR and offshore wind accelerator, you were deeply engaged. But do you have any follow-up comment on the scanning LiDAR?
Yeah, I think I definitely agree with what Neil said. In the Dublin Bay trials that we did under the Offshore Wind Accelerator program for scanning LiDAR, we deployed 4 scanning LiDAR systems from 2 different manufacturers. They were designed to 2 different scanning ranges. I think one was around 10 kilometers, one was around 15 kilometers. And I think, it's fair to say that in the about half to 2/3 of the distance was fairly good data, but then beyond that it was getting very, very low quality data. But they were scanning to those ranges and beyond as well. So it really means that scanning LiDAR is limited to quite near shore application, because I think, yeah, I would probably think there's probably not very any systems that can reliably scan at around 10 kilometers or more on a consistent basis. On the dual Doppler point, we've actually published all these results, so they are on our website. There's a report published from the scanning LiDAR trials at Dublin Bay. But we found that the dual Doppler was effective and worked, but didn't increase the range massively at all. So yeah, there are advantages to dual Doppler, but also so using 2 scanning LiDARs, but it's obviously twice as expensive, and scanning LiDARs are a lot more expensive than floating LiDAR systems, generally speaking, and especially the ones that have longer ranges are a lot more expensive, and a lot larger as well, so difficult to find somewhere to put them. So yeah, there are different pros and cons. It really depends on the kind of deployment, the aim of the deployment, the site conditions, and everything.
One issue which I meant to touch on was synchronization. So if you really are trying to look at the same point with 2 beams simultaneously, you need very accurate synchronization between the LiDARs. if you don't have that and you're effectively just scanning independently with two different systems, your uncertainty increases as a result. So it's another thing to factor into the campaign design.
はい、ありがとうございました。メガさん、ニューさん、ありがとうございました。まだたくさんご質問ございますが。
So Megan and Neil, thank you very much for that. We have so many more questions, but we are already exceeding the allocated time. So for the questions which have been included in the Q&A box, I would like to summarize them, and we would like to come back to you at a separate date. I'm sorry we have so many questions, and we haven't been able to cover everything. And thanks to the support from our Carbon Trust, we would like to come back to you. Hirata-san and Faizi mentioned that several webinars have been held, and this is actually the second time, and we are hoping to have series of these webinars going forward as well. If you have any specific topic you would like to cover, we would like to take that up. And thank you very much. And we would like to return the microphone to Yamaguchi-san. Thank you very much, everyone. Thank you very much. Just like you mentioned, we have not been able to respond to your questions, and we would like to come back to them at a later date. And if you have any requests for the upcoming webinars in the future, we hope that you will jot down in the questionnaire as well. I think that we had a quite intensive session in the Q&A session. I'm sorry we extended the time, but I think we covered all the agenda items for today. So lastly, we hope that this is an open style or questionnaire that we will be sending you. So we hope that you will send us the request. Thank you very much for staying until the end of the seminar. In the upcoming seminar, I look forward to see you again, and I would like to ask for your further support. Thank you very much.